I am so excited that we, even in this time where visiting campus isn't possible, that we have an opportunity to talk a bit about Swarthmore, and in particular, talk about some topics in gravitational waves and black holes in a bit. But I want to start off just giving a brief summary of the natural sciences and engineering division, of which the physics and astronomy department is one of the departments in this division of the three divisions at Swarthmore: natural sciences and engineering, humanities, and social sciences. So just briefly, these are the departments that are part of the natural sciences and engineering division. And one thing I want to point out, and something that I'll mention a bit more detail in relation to physics and astronomy, there are many, many opportunities to engage actively in research through research assistantships in all of these different departments. And that kind of brings me to say one quick thing about studying natural science and engineering at a liberal arts college. So these opportunities are geared towards undergraduate students. So we are all expert at both teaching in the classroom and also having research in our fields that is amenable to having undergraduates actively engage with our research and collaborate with us. Another aspect that really drew me to wanting to be a faculty member as a physicist at a liberal arts college is that students at a liberal arts college, whether they are majoring in natural sciences or engineering or humanities or social science, just by being at a place that is so intellectually rich and with the opportunities to be exposed to all sorts of different topics and ways of thinking, really become very well-rounded and knowledgeable about the world. And if there's anything that we need right now, well, there's a lot of things that we might need, but having scientists in the world who are knowledgeable about things outside of science and understand that science does not work in a vacuum, but is a human endeavor and activity, and how that relates to all sorts of other aspects of being a part of communities and being a part of the global community, is to me one of the most rewarding and important things that we do as teachers and scientists at Swarthmore. So let me tell you just briefly a little bit about specifically physics and astronomy, which is what I know the best. So right now, and for the past several years, I have been teaching the introductory course for people who are potential majors or minors in physics and astronomy. And it is known as Physics 5. And in this course, we talk about special relativity and quantum mechanics. And I want to say again, this is our introductory course, and we've designed it so that students coming with a whole range of mathematical backgrounds this is material we've put it together in a way that's accessible. It's challenging to all of the students who take it, and really introduces students to two of the most important aspects of modern physics and two of the most surprising. And that's a very unique aspect of our curriculum at Swarthmore, that we start off with this introductory course. So part of what I'm going to talk about in a bit about gravitational waves and black holes, I actually use the same or similar slides for the class that I'm teaching this semester for Physics 5. And I also want to just mention the specific research opportunities that we have in the department. We have opportunities in plasma physics, materials science, granular materials, biophysics, massive stars, exoplanets, cosmology, and gravitational physics. Many, many opportunities, both experimental and theoretical work that is going on in the department itself. And I finally just want to mention all the variety of careers that students go on to work in after getting a degree in natural sciences and engineering at Swarthmore. There are some students who go on and get advanced degrees and go into academia. Students go into industry, finance, policy, nonprofit law, and so forth. And one of the most exciting things that I've had the opportunity to experience at Swarthmore is seeing students go off into all these different areas and learning about their experiences, bringing their knowledge of physics, let's say, and seeing how that maps onto work that they're doing in policy or a nonprofit, and so forth. So I'm excited afterwards to answer questions as best I can, generally about natural sciences, engineering, or questions about physics and astronomy at Swarthmore. So with that brief summary of what we're doing at Swarthmore in our division, let me move on and talk specifically about some of the most exciting physics and astronomy that is happening today. And it relates to LIGO, which is a gravitational wave observatory, Virgo, so LIGO is in the United States, Virgo is in Europe, and the fact that we are in an age in which we are learning so much about black holes. And we're gonna focus on gravitational waves, but at the end, I'll touch upon some of the other things that we've learned recently about black holes. So we're going to start with a brief introduction to what a gravitational wave is. And to do that, let's start just with basic division between the two different types of waves that we have in physics, in the world. The two different types of waves can be distinguished in how the disturbance of the wave is oriented relative to the direction that the wave is traveling in. So the picture that I have here is a disturbance that is perpendicular to the direction that the wave moves in. This is called a transverse wave. And then the other type of wave that we have is called a longitudinal wave. And this is where the disturbance is parallel to the direction in which it moves. Gravitational waves are transverse waves. And here is a diagram of a way of representing what a gravitational wave looks like. So this gravitational wave here is traveling in this direction up the z-axis. And you can see that it's represented by this diagram where these arrows are stretching out horizontally and then stretching out vertically and then alternating as the wave moves down the z direction. One way to get at answering what is a gravitational wave is to ask, what does a gravitational wave do? And so in a moment, I'm going to play an animation that shows what would happen to this boat if a gravitational wave were traveling out of the computer screen that you're looking at right now. So the gravitational wave would cause the boat to stretch in one direction and squish in the other and then alternate. And this is actually the stretching and squeezing of space-time itself. But in terms of what it would do to an object like a boat, it would cause it to stretch and squeeze. Now, this gravitational wave animation I'm showing you here is definitely not to scale. We're going to see in just a little bit that gravitational waves that we detect are causing very minute stretching and squeezing of space-time. So here I've exaggerated it so we can actually see it. So let's take this image of a boat stretching and squeezing and see how that is used, the stretching and squeezing is used to actually detect gravitational waves. So I'm going to play an animation in a moment of how a gravitational wave detector works. And this particular detector is called an interferometer. This is a simplified version of what the gravitational detectors that we currently have, how those gravitational wave detectors work. So before I play the animation, I want to describe what these various pieces are. This cylinder here is a laser. So we're going to have laser light coming out of this cylinder, and it's going to travel and come to this object here. We're seeing it edge on, but this is a half silvered mirror. So this mirror is going to allow half of the laser light to travel in this direction. The other half of the laser light will travel in this direction. And that light is traveling to two mirrors that are represented by these circles. So the laser light is going to bounce off of those circles, come back from both of these mirrors, and then it's going to combine and end up over here at the square. And the square is just a camera. It's just a way for us to image what the light looks like coming out of the mirror in this direction. So let me play the animation, just a bit of it, and then we'll talk about some of the physics that's going on. So laser lights coming out, bouncing back, and going to that camera. In a moment, we're going to see what happens if a gravitational wave were coming down in this direction. And remember that gravitational wave is going to cause parts of this instrument to squeeze and parts of it to stretch. So we're going to see these mirrors move. And that squeezing and stretching we can represent by this amplitude h. We're going to come back to this in a moment. And that just quantifies the fractional change in the distance between these mirrors as the gravitational wave passes by. And as that happens, watch what's happening over here at the camera, what the camera sees. So as that gravitational wave passed by, the camera sees alternating bright and dark, bright and dark. And this bright and dark that the camera is seeing is what gives this instrument its name. As I said before, this is called an interferometer. And what's happening is as the gravitational wave passes by, the light coming out towards this camera is alternately constructively and destructively interfering. So that just means that the light is either adding up from both sides of this interferometer or it's canceling out. And so that causes this bright and dark pattern. So this animation actually shows us a representation of the laser light itself as a wave. So here it is bouncing off of that mirror, coming back. And at this point, without a gravitational wave, the light coming from both of these mirrors are in different places. So one is a peak where the other is a trough. So when they add together, you get no light coming out at all. But then when a gravitational wave passes by, it's going to cause this to now become constructive and then destructive interference alternating. And we see this bright and dark image that this camera is measuring. So one of the things that I want to impress upon you is that even though this description of how a gravitational wave detector works seems simple, we're going to see in a moment that the gravitational wave detectors that we have are pretty clearly the most precise instruments we have ever made in the history of humanity. And that's because these gravitational waves are so tiny. Their effects are so small that we have to build instruments that have never been imagined before the last 20 years when these instruments were first designed and built. So before we talk about that, I want to kind of give you a sense of how, what a gravitational wave looks like as it were a real cartoon of a gravitational wave passing by the Earth. So one of the things I want to mention is that the interferometers that make up this collaboration called LIGO, there are actually two of them. One of them is in Louisiana, the other one is in Washington State. So the first gravitational wave that was ever observed had a frequency of about 100 hertz. That means it oscillates once every 100th of a second. We can combine, and some of you may have seen and studied waves, we can combine frequency and wavelength. When they multiply, they give us the speed at which the wave is traveling. And it turns out that gravitational waves travel at the speed of light. So once we know the frequency of these gravitational waves, we can work out what their wavelength is. So in this case, these gravitational waves have a wavelength of 3,000 kilometers, which is about the size of the United States from north to south. And the gravitational waves that were observed came from the south of the United States and washed over the Earth traveling north. So they hit the Livingston interferometer first and then arrived at the Hanford interferometer. So there was a delay of about 7 milliseconds between Livingston and Hanford detecting these gravitational waves. So now let's look a little bit at the facts or the things that LIGO is able to do. As I said before, the effect of these gravitational waves are so tiny that we need instruments that are by far the most sensitive instruments that humans have ever made. And just to represent that in a way that is insane, these mirrors that we saw in that animation are 4 kilometers apart. But in order to measure the gravitational waves that pass by the Earth, we need to monitor their distance to within 1/1000th the size of a proton. That is mind-bogglingly sensitive. This instrument has to be unbelievably sensitive. One of the facts that I find amazing is that the mirrors themselves are made of 10 kilograms of pure sapphire. And they're vibrationally isolated with this extremely complicated and active vibration isolation system. So really amazing engineering that goes into this. And just to express some of the other amazing things that LIGO can measure. So for LIGO that's in Washington State, there's logging activity several miles away, and every time one of those trees fall, the instrument is so precise that we can actually see vibrations from those trees hitting the Earth, and then that vibration traveling through the Earth and arriving at the LIGO site in Washington State. And then the vibrations in the continental plate due to ocean waves for the Louisiana LIGO site are detected. You can actually see the effects of waves hitting the continental plate. Really extraordinary instrument. So that's a little bit about the way that we detect gravitational waves and what gravitational waves are. The other part of the story is to understand a little bit about where gravitational waves come from, what produce gravitational waves. And the typical source of a gravitational wave is a pair of black holes that orbit one another. And as they're orbiting one another, they send out these gravitational waves, these ripples in space-time that then move away from this pair of black holes at the speed of light. So for the black holes that we've seen in LIGO, they are at cosmological distances, billions of light years away. And then over time, those gravitational waves move away, and at some point they wash over the Earth and we see them, where we measure them with LIGO. As the gravitational waves are emitted from these pairs of black holes orbiting each other, those gravitational waves take away energy. And as energy leaves the system, the black holes get closer to one another. And exactly like as an ice skater, when they're on the ice and spinning and they bring in their arms and they start to spin faster and faster, as these black holes get closer to one another, they spin faster and faster, emitting even more gravitational waves until the moment when the 2 black holes merge into a single black hole. So for, I would say, 50 years, we could have told the story that I just told you as a cartoon. It was actually not really known exactly how this process would work out in terms of the predictions of Einstein's theory of gravity, which is our best understanding of gravity is Einstein's theory of general relativity. And it was only 15 years ago that people were able to take the equations of general relativity and put them onto a computer and do a simulation, because that's what's necessary to work out this physics in detail. But since people have done that, put in that hard work, we now have amazing animations in order to visualize what's going on. So let me briefly describe, this is a complicated animation, so let me describe what's going on. At the top here, as indicated by this label, we're going to see the black holes orbiting each other. At this lower part here of the animation, we have 3 different pieces. We can see the curvature of space-time, and that's just shown, this is like a sheet, and it's as though we've bent the sheet down. So the further the sheet goes down, the more curved space is. The colors here represent the flow of time. So time actually flows at different rates in different locations in this calculation. And this is my favorite. There is a velocity of the flow of space. These are amazing concepts and really redefine our concepts of space and time. And I want to just emphasize, as I mentioned before, that this introductory physics and astronomy class called Physics 5, we don't go into general relativity too much, but we do go into special relativity, which gives us a basis to understand what these concepts mean. On the bottom here is something that's called a waveform. This is showing what LIGO would measure once the gravitational waves from the system traveled from where the system is all the way to the Earth. So with that, let me play this awesome animation. So the two black holes are orbiting each other. They're losing energy to gravitational waves. They're coming in closer and closer, spinning faster and faster until the moment that they merge. So this is what it looks like for two black holes to merge. And then after they merge, they wobble a bit and then they settle down into a rotating black hole. What's really unbelievable is that 15 years ago was the first time we could simulate this. And 5 years ago, we measured these gravitational waves and they agreed with the calculations very, very well. So we've really entered a completely new era of physics and astronomy where we are detecting gravitational waves and we're learning about black holes. Before I talk a bit more about some of the other ways in which we're learning about black holes, I just want to mention the fact that these interferometers that I'm talking about are only one piece of the gravitational wave puzzle that we have, we've either are currently using or we are planning to build in terms of different ways of detecting gravitational waves. So I've been talking so far about terrestrial interferometers. And what I'm showing here in this bar is that gravitational waves, just like the electromagnetic waves that we're using right now to see this, come in a wide range of frequencies, which is the same thing as saying a wide range of wave periods. So terrestrial interferometers are sensitive to wave periods on the order of milliseconds. There is a plan in the next 10 years to put interferometers out into space. And that way of detecting gravitational waves would be sensitive to gravitational waves with wave periods between seconds and hours. There's something called pulsar timing, where we use rapidly rotating neutron stars to detect gravitational waves. And I'm actually a member of a collaboration called NanoGrav doing this in North America. This method of detecting gravitational waves would be sensitive or is sensitive to gravitational waves with wave periods around years. And then finally, looking at gravitational wave periods on the order of the age of the universe, we can use the polarization of what's known as the cosmic microwave background. This is the afterglow of the Big Bang. And this is actually what most of my research focuses on, the physics of the cosmic microwave background. And I've done some work looking at how we can use the polarization of this afterglow of the Big Bang to detect gravitational waves. So one of the things that's really cool is, besides the fact that we have a range of ways of detecting gravitational waves with different wave periods, we have different sources produce gravitational waves with different wave periods. So binary black holes, as I talked about before, produce gravitational waves measurable by terrestrial interferometers. So do rotating neutron stars and possibly supernovae. One of the most interesting sources of gravitational waves is the possibility that there may be extremely massive black holes at the centers of galaxies that form binaries and produce gravitational waves. Those would be measured by pulsar timing arrays and by space interferometers. And then one of the most extraordinary sources of gravitational waves may be the quantum fluctuations in the early universe. And this, if it's out there, will most likely be detected by the cosmic microwave background. So there are some things that we know on this picture. Most of this is in the future, are things that we have yet to measure. And there are things that we have yet to even think about in terms of both the sources that may be out there, as well as new techniques that will measure gravitational waves. So a lot of exciting things. One of the things I want to mention is that our terrestrial interferometers, it's a global effort. So we have our interferometers in the United States, LIGO, Hanford, and Livingston. Virgo is located in Italy. There's another interferometer that is going to be turned on and used soon called Kagra in Japan. And then in the not so distant future, there's a plan to build LIGO in India, an interferometer in India. So this is not only exciting for the things that we're learning about the universe, but also is bringing different scientists across the world together to work in collaboration to measure these gravitational waves. So just to give you a quick summary of where we are in our understanding of black holes, this is a really interesting figure that shows all of the known black holes as a function of their mass. So on the vertical side here with these lines is the mass of these black holes in units of the mass of the sun, or in solar masses. Each of the blue circles here represents black holes that have been detected through the gravitational waves that they've produced. These purple ones have been detected using electromagnetic radiation, or light. And then down here are neutron stars. And one of the most extraordinary detections that was made using LIGO and other telescopes is that we've actually measured 2 neutron stars that were in binary systems, just like the black holes I talked about before, but they came together and smashed into each other and produced not only gravitational waves, but also light. And we learned so much about the physics of neutron stars, which are very exotic on their own. And then we still have question marks as to what those merged objects became. And I want to end by just talking about some of the other ways in which black holes are currently being learned about in physics and astronomy. So one that you might have heard about in the past year is something called the Event Horizon Telescope. This is a global network of radio telescopes that actually imaged a black hole for the first time. So this collection of radio telescopes looked at a galaxy, a fairly nearby galaxy called M87. And this is an image of the galaxy using, not with the Event Horizon Telescope, but with a different telescope. And then we have zooming in further into the center of the galaxy, and we can see something interesting is happening. There's this jet in the galaxy. And then if we zoom in using the Event Horizon Telescope, we can actually see the shadow of the central black hole that is driving this energetic jet and all of this material coming out of the center of that galaxy. So I'm going to wrap up there. There is so much that we have yet to learn about black holes, about gravitational waves. It's an extremely, extremely exciting time to be thinking about these things.